we're here to talk about multiplication and where it sits within the normal progression of the four operations that we do in mathematics. So we're used to the idea of adding, taking away, multiplying and dividing, and I think that we all experience that within our classrooms the fourth operation, division, is the point where students sort of throw their hands in the air and say that they can't do it. I don't know my divisions is something I quite often hear as though it's some sort of topic that needs to be memorised and understood. Now, we'll come to division as a specific idea for a separate poster, but I want to talk about the progression through from addition to subtraction and then the jump to multiplication, because I would suggest that it's the jump from addition to multiplication is where the problems that students encounter are sort of fomented and begun, and then the division issues are actually in many respects the symptom of that. So I'll try and explain it in a bit more detail. First of all, as we know, everything that a student learns is based upon what they've already understood. So the first things that students will actually learn to do before they do any arithmetic is they learn to count. So we're all used to the idea of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, counting on fingers, and then it becomes natural. But once they count, they can begin the arithmetic. So they can do simple addition, which will be based on counting. So 3 plus 4, 1, 2, 3, 4, 1, 2, 3, 2, 3, 4, 5, 7. So counting allows them to add, and then eventually the addition will become innate and they will know. So you ask them what 3 plus 4 is, and they'll tell you it's 7. They don't even have to give it any real thought or calculation. Once they've got the idea of adding, then again, subtraction becomes part of the process. And it's usually, as far as I'm aware from all the visits and discussions I've had, relatively straightforward. And again, often based on ideas of counting. So 7 take away 3, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 1, 2, 3, 4. So again, we're basing the progression of arithmetic on what's previously understood. What I would argue is at this point, this is where the potential misconceptions begin. Now, I'm just going to take a little sideways step here to try and understand what we see in the high school quite a lot. And there's a particular question that I enjoy asking students, which is 14 multiplied by 12. Now, obviously a lot of students will arrive at high school able to tell me the correct answer, but a significant number, if it's purely as a mental arithmetic question, might tell me that the answer is 108. Now, there is a logic to that answer, because they understand that there is a 10 multiplied by 10 component to the question, which is worth 100, and they understand that there is a 4 multiplied by 2, which is 8, hence the 108. But they've missed out on the full picture, which I'm going to try and describe. The other thing that we'll see is if they're allowed a pen and paper, is that they might go for example, a large 6 14s, add that up, and once they've got that answer, they then double it, which they know which will get them the correct answer. But the point is, it's addition, it's not actually multiplication. And also, if we gave them a larger question like 53 multiplied by 47, they would just give up, because they can't be bothered writing out that many 53s in order to do the repeated addition process. So there's a breakdown. So this is something that we see, which is partially correct, but it doesn't have the whole picture. And then this one here is actually using addition as a proxy for multiplication, and they're only focused on the answer. Okay, so the poster that we've created is to try and bridge the gap between adding, which the students seem to be able to cope with relatively well, and genuine multiplication, rather than using repeated addition as a proxy. Now, first of all, if we had something like 4 multiplied by 3, which you would see in the primary schools quite a lot, everybody, and I mean everybody, would first approach this like this way. 3 lots of 4, or 4 lots of 3. So 4 plus a 4 plus a 4. There is absolutely nothing wrong with this idea at all. But we need to be clear that what we've done is that it's repeated addition. So we've gone 4, we've added another 4, and then we've added another 4. So effectively, I'm holding a line that has the value of 12. Okay, so addition is simply adding to something we already have. In its simplest form, a line is the best way to represent it. So 4 plus 4 plus 4. And my answer is 12, or the value is 12, which often for a student is good enough. And that's all they need to do. What we're hoping to create is this idea that, in fact, and this is the first design on the poster, is what we all understand as the array model. And the array model is the genuine multiplication idea. So 4 multiplied by 3 is 4 multiplied by 3, and I've actually created a space with the value of 12. And this is, if you like, true multiplication. So in the simplest form, when you first introduce this symbol, make sure it's introduced with this visual. And again, I repeat, don't worry about the fact that you have to first talk about repeated addition. The students will understand it. But rather than sticking with this, move to the visual picture of the arrays. Because if there is this confusion in the student's head between multiplication and addition, they replace, even though they're seeing a multiplication symbol, they're replacing it conceptually with ideas of addition, and often they get stuck there. For example, if we have a question like 12 multiplied by 8, we still see far too many students which is the correct answer, but there's no actual multiplicative ideas in that calculation there. They've conceptually replaced this with addition, and we want to bridge that gap. And there's a number of reasons for that. If they don't bridge the gap, then things like fractional thinking becomes difficult, and division becomes near impossible, and then the transformation and the shift from number to algebra is incredibly difficult, if not fundamentally impossible, really, because they don't truly understand what it is they're trying to represent in a general sense, because in these very specific answers, they've taken themselves into a wrong position. So, again, whenever you're dealing with the idea of multiplication, try and get the representation to be visual and to be dimensional. Multiplication, 12 multiplied by 8, we are holding a space that has the value of 96, rather than a 12 and 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 a 12, which is worth 96. And try and avoid the argument, well, it's the same answer, so what's the difference? Because this is a dead end. The student has got very, very few options to take this thinking further, and most NCA senior maths will become incredibly difficult for them. Okay. So if we're going to the question such as 12 multiplied by 8, here is the array that I've just drawn out. Now that's quite painstaking, and you could actually get students to do it with squared paper or dotted paper, so there are ways that we can do it. But again, it's how do we then get the value from it, and this is where we use our base 10 number system, because we can split this down into 10 multiplied by 8, and then here we have 2 multiplied by 8, so here we have 80, here we have 16, and now we will add together our final values to get 96. But the important thing is that what we've seen here is that they understand the visual idea, the geometric idea behind their multiplication. And they're actually seeing multiplication, seeing it and conceptualizing it for what it actually is, rather than just a technique to get a number. We're actually creating a space, and the space has a value of 96. So I'm just going to share a conversation I had fairly recently with one of my Year 9 classes. And I had this question on the board, and the entire class were confident that the answer was 20, which is obviously correct. But that's not the interesting thing. The interesting point is when I picked up my abacus and actually said, show me the question on the abacus, the first student who volunteered came up and simply did that. They showed me a 4 and a 5 on the abacus. And there was a great deal of agreement in the class that this was correct. So what they were seeing in the question had no visual underpinning at all. I made the point to them, but you've just told me that 4 5s are 20, so where's the 20? And a second student sort of said, oh, okay, and then showed me that. And again, there was a lot of agreement that this was now correct, because this is 20. So there was a big disconnect between the symbolism and the question that was being asked, that they understood the value of everything, but they had no picture. It took a while for me to get them to understand that in fact, this is what they should have seen. This array has the 4 and the 5 in the initial question, and it has the 20, which is the solution to the question. And so it was clear to me that although we had a sort of a superficial understanding of being able to do multiplication, even with mental arithmetic or with some recall, there was a real roadblock to how they could move forward with it. And again, it was this idea that there was an array, there was a space being created, and the value of the space is equal to the dimensions, and the dimensions of the question. It all links from one end to the other. So again, the simple idea that they were lacking is that there were components of the question that are in fact dimensions of a space. And ultimately that is the picture that they needed to have in their head. Whereas I could see them actually just either, well, for 4 multiplied by 5, there was instant recall. It was one that they understood, but even for slightly more difficult ones, I could see the repeated addition coming in. And it's the idea of drawing a rectangle to represent and show your multiplication calculations is the key to how we're trying to do this maths at Monterey High School. So I had previously shown you this question 12 multiplied by 8 as a series of arrays as dots, which is painstaking and time consuming. At the lower levels, this is what will need to happen to embed the idea, but eventually our students can understand that what we've got is a space, and these are our dimensions. One side is 12, the other side is 8, and we need to know the value of this space here to get the answer to our calculation. The next stage that they'll understand is that a number such as 12 can be broken up into our place value statements. So we've got a 10 and a 2. And most of our students will happily tell you that 8 10s or 10 8s is a value of 80, and 2 8s is 16. And so now we have our total of 96. And again, once the students start to see it, it becomes a very powerful way of doing these multiplication questions. If I just return to this question, which when I ask it as a mental arithmetic question, I often get the answer of 108. The answer of 108 isn't completely incorrect. It's because students have a partial understanding of how the numbers combine. But if they see 14 multiplied by 12 as a rectangle, where one side is 14 and the other side is 12, they need to gain the space. And again, we can think of 14 as being 10 and 4. And we can think of 12 as being 10 and 2. And again, I'm not worrying about things being to scale, but it's the idea that we have the larger rectangle in blue, and I want to find the whole value of it, but I've got these distinct subsections that are in themselves relatively easy to calculate. This is 10 lots of 10. So this has the 100, which if you remember, the students are aware exists. They know that there's a 10 times 10. This smaller block down here is the 2 multiplied by 4, which is the 8 that the students are aware of. What they don't see in their mental arithmetic is there are these 2 missing spaces. This one here with a value of 40, and this one here with a value of 20. And so the sum of these spaces is 168. And again, they partially understood it. They knew there was a 10, they knew there was an 8, but once they see the space and they understand that these points are going to be there, then they're able to not just find the answer, but they're able to actually understand what is actually happening, the why of the whole multiplication process. And we can actually take this even further, just purely with whole numbers. For example, we could go something like 37 multiplied by 15. Now again, this is it's going to be a rectangle. I'm going to jump a few spaces a little bit, but hopefully people can understand. That we have these, again, 4 subgroups. Okay. Now again, when we're working in class with these sorts of questions with the students, we're very careful with our language about how we describe the multiplication process. It is very easy at this point for sort of the lazy adding on zeros to creep into the calculation. What we try to do, and I strongly recommend we do it, if we have something that is 10 multiplied by 30, we think of it as being 3 multiplied by 1 is 3. So we have 3, and then it's 10 times bigger and made 10 times bigger. So it's laborious, but it instills this idea of it's numbers multiplying to become larger values, not adding 0, which in itself doesn't actually have any mathematical meaning. Adding 0 actually changes nothing. So we want that language to be kept away from the calculation. Again, this would be 7 times 1, which is 70. And obviously some of our older students would know this one intuitively. We're not going to stop them if they just happen to know it, but when we're doing, for example, we might do 40 multiplied by 30. 4 times 3 is 12, made 10 times bigger, made 10 times bigger, and get them to be very clear about what they're doing. Here, 5 lots of 30, or 5 times 30, or 5 multiplied by 30. 5 multiplied by 3 is 15, and then 15 made 10 times bigger is 150. And then here, 7 5s are 35. So now we have 300, 450, 520, 555. One of the important points of what we're trying to create here with this use of multiplication as a rectangular space isn't just to be able to do numerical calculations faster and easier with clarity. It's actually to have a golden thread where their thinking will, without having to learn new concepts, will carry on through high school and beyond. So if I just return briefly to the 40 multiplied by 12 is 168, this is just to remind us of that multiplication model using number. But what we can now look at is a question like this. Now, this is known as a quadratic expansion in the textbooks. It is just a multiplication. And we're just going to remind you here, this was 14 multiplied by 12, which was 10 and 4, multiplied by 10 and 2. And we had our subspaces. This is a multiplication. It's something, and we're using the word x, plus 4, multiplied by something and 2. Because it's a multiplication, it is going to make a rectangular space, because that's what multiplication creates. And one side is going to be x and 4 long, and the second side is going to be x and 2 long. Now, This is x multiplied by x, which we usually write as x squared, or x to the power of 2. This is 4 multiplied by x, which we write as 4x in our mathematical shorthand. This is 2 multiplied by x, which is 2x, and this is 4 times 2, which is our 8. And just as here we need to add up all the individual values in our larger space, here we have x squared. We're going to add on 4 x's and 2 x's and 8. The only like terms, I don't like using the phrase, but this will become x squared plus 6 x's plus 8. These are the dimensions of our rectangle. This is the area of our rectangle. And hopefully you can see that it is exactly the same process. So the ideas, the concepts haven't changed. All that's changed is the value or the appearance of the numbers or variables that we're putting into the calculation. And we know that when our students understand this concept, the shift from this form of multiplication to this form of multiplication can and will happen very, very quickly.